Good morning, and welcome to lesson number 16. Today we're going to be looking at steel design checks. So, first of all, what is a steel design check? Well, hopefully, if you've taken ECI 132 with Dr. Convende, then you recall that you did a whole bunch of basically design check calculations using the LRFD design codes. So that's pretty much what we're going to try to do in SAP. And SAP actually has a very nice interface of already doing this for you, and it's called the Start Steel Design Check of Structure. So you can go up to this nice I section, view revise preferences, and pretty much this is more or less what you're probably familiar with. It's using the AISC design code. You can probably select something else, but I'm just going to do AISC IBC 2006, and it'll have, pretty much it's using LRFD. It has your phi factors and all that good stuff. So that's what I'm going to be using in this lesson. Now, in order to use the steel design checks properly, we need to specify which load combinations we're going to be looking at. So you have to select the proper load combos. Now, it'll automatically say have this box checked, but you don't want this checked. This will give you crazy, stupid results. So don't check this box and import your own load combos. So this actually requires that you define load combinations rather than just cases. So if you remember from the end of lesson 11, the beginning of lesson 12, we looked at load cases and defined load cases, but we didn't necessarily define any load combinations. But it's actually pretty easy to define load combinations. You can just go to pretty much add a new combo, and then you can pretty much pull from the existing load cases in order to define a new combo. So you could just do case 1, step 1, and then call it combo 1, step 1. Which is pretty much what I've done here. I haven't looked at step zeros just because that's probably not going to be a limiting case in my model. And what I'm going to do is, now that I have my combos defined, I'm going to run my model. And I'm going to go to pretty much select design combos, make sure I have all my combos selected, and make sure when you run the model that you had your combos selected. I don't think in this case it actually shows the combos, but you can assume that it probably run them. Just because it ran the cases. Now go to Start Design Check of Structure, and this is where the real meat of the lesson is. So here we go. You get a nice visual representation of pretty much what amounts to the demand to capacity ratio for each member. So pretty much the demand to capacity ratio is just kind of saying that if you have that number less than 1, it means that your demand is less than the capacity of your member, which means your member should be okay. It has more capacity than you're supplying with demand, I guess. But if you have the number above 1, if your member is showing up in red, then that pretty much means that your member is suffering a larger demand than it has the capacity to hold. So that member will likely fail. So how is it going about determining what those ratios are? You can see, most of these are pretty good, but, specifically these top chords on these laterals are having some issues. So let's go ahead and select one and right click on it, and it'll come up with this nice menu, and pretty much it'll have, the whole list of all the combos that you've run, and it'll show, at what location along that particular combo you're having that particular ratio calculated. And the main ratio is the moment interaction check. So this is pretty much, if you remember from steel design, the moment interaction check combines the effects of axial load on the member with the major axis and minor axis bending effects. So this is the overall kind of ratio that's being read out. And this C here is kind of just denoting that this member is in compression for this particular loading case. If it was T, then it would mean it's in tension. So we know this member is basically has a ratio of 4, which basically means that our demand on this member is 4 times its capacity, which is very bad. Not very good at all. And it's also in compression. And most of that is coming from axial demand, not necessarily so much from the major axis or minor axis bending. So To get a little bit more detail, let's go to the Details tab, and you can see, there's some specifications for what the frame is, some of the properties of the frame, and then some of the LRFD specifications. You get your fee factors, everything. You'll have some design messages if your member is failing, and in this case, it's saying, obviously, my section is overstressed, and I'm getting a warning that based on the ASC design codes, my KL or R-min or slenderness ratio is greater than 200, which is, maybe you remember that criteria. Basically, you need to have kind of a limited slenderness of your member. Now, you can see a whole bunch of other things. Here are the actual demands on our members. So PU is the axial demand in compression, and it's calculating our demand to capacity ratio here. And you can also see the actual axial capacity in compression. So phi times PNC, C for compression. This is our axial compression, or axial, compression capacity, which is about 0.2 kips. But we're applying about 0.86 kips, which is bad. So if you remember, what we need to do is then increase our axial capacity in compression. And how do we do that? Well, we could try to increase the cross-sectional area of the member, but that's not going to do a whole lot. Really, the meat of how you can improve your axial capacity and compression is by improving your KL over R-min ratio. So K, of course, is the fixity coefficient. So maybe you had like a top chord member that was pin conditions at the ends. We could try to maybe say change those pin connections to tube-in-tube connections, and then it would have a greater fixity, and thus the K would change, and we would get basically a higher capacity. L also, so the length of the member. Maybe we could try, instead of looking at a really big member, then try to break it up into maybe smaller or maybe bulkier members. So L, might be something that you could try to reduce the length of the member. But really what we're going to be looking at is R, which is the radius of gyration, or the least radius of gyration of the member. And basically, in the case of most of the tubes that we're going to be looking at, the radius of gyration is almost equivalent to the radius of the tube. So if you can increase your tube diameter, then that pretty much means you'll be increasing your axial capacity in compression. So let's try that. I'm going to go ahead and unlock my model. I'm going to select those members that were failing on these laterals, and I'm going to go to Assign Frame Sections. But before I do that, I'm going to check my extrude view to see what these are originally. It looks like it's maybe the 1/2 inch tubing. So, okay, I'm going to go Alt-AFS to Assign Frame Sections. I'm going to change these to maybe the radius of, I guess this is round tubing, 1 inch diameter tubing. Let's see what that does. Alright, it looks kind of bulky, but I don't know, maybe that'll be good. So let's go ahead and rerun our model, and then go to our steel design checks and see if that did anything. And it looks like, yeah, we did a pretty good job. So now our members are about 60% of their total capacity, which is, not bad. So we're not failing. It's still in compression. Axial case is still limiting, but, we significantly improved our performance for those members. So you can kind of go through the bridge and maybe look at members that you think might have an issue, like, these webbings here might be something that you'd probably replace with something bigger. And, kind of use your intuition about how to fix those problems. But the thing that I want to mention, though, is you should really try to be as wary of using this whole design check process as you can, because just as a historical reference, if you recall, in 2014, right before mid-pack, Quincy had kind of done a last-minute check of the bridge on these two members, which originally were very slender. And you probably remember we had to bulk these up a little bit with the kayaks, as we called them. And pretty much, the problem that we were having was these members were failing in compression. But Quincy had kind of originally proposed that maybe we do just kind of like these tumor things that just kind of bulged out right in the middle of the members. The problem with that is basically the whole design check process in SAP actually uses or it goes about calculating pretty much what the actual capacities and everything, and does all the checks for each member on a frame section by frame section basis. So it would look at this frame section, it would get its overall length, and use that for its KL over R min. But what if you said maybe you went into your CAD model and had originally drawn this member from this point and then ended it here and then drew another frame section from that point to there, so it would be pretty much discontinuous. There'd be two frame sections. Then you would only have, maybe in this design check, you would look at just this one member and it would be using this length, half the length, for its KL over R min calculation, which is completely incorrect. It would be the same kind of configuration as if you had drawn this single member, but it's saying that maybe now this member, since it's only using half the length, that now it's totally fine, but it's not. So you have to really be careful about how you set up your model, and just be overall wary of using the design check. Even Dr. Convinde was kind of wary when I had brought up the design check in SAF. He kind of didn't seem to be very approving of this whole thing. But it does give you a good idea of what members are probably going to be in trouble, so you can fix those at least right away. And then hopefully, other things that you're a little bit worried about, you can use some other things to try to make sure that the bridge isn't going to fail in those other mechanisms. So hopefully that was helpful. Definitely do this for all of your models, and yeah, happy hunting down your failing members. All right, good luck. I'll see you later.